Okay, we're going to hit back at it here. We've got about 4 more examples left on this notes page. We're going to try to cover the next 2 today. And this is when picking out the formulas are going to be a little bit more tricky. And this is why, as you look at the problem, and we're going to pick up with example D, number 4 here, you're going to find that you are not going to see a formula that is going to exactly match this integration problem. Okay, despite the fact that our goal still remains the same. The goal is to get the left side of whatever formula you choose to eventually look like this original integral problem that we are given here. Okay, now here's matches the most difficult part of your integral. So for example, looking at this problem, if we had to make a distinction of which aspect of this integration problem feels like is the more complicated part, we would definitely say that the denominator is more complicated than the numerator. Okay, and so here's what we're going to look for. When we flip back to the very front of this notes page and we have that list of formulas, our focus is going to be exclusively finding a formula where the denominator of this integral is going to match. Now you're going to notice something when you look back, and I'm going to go ahead and scroll on back to the front page here that has all the formulas, because I went ahead and I copied our problem off to the side here so that we could see it. I left this up here because our goal is to, right now, you should only be looking at the left side of these formulas. The right side, once you've chosen a formula, the right side then becomes your answer when you make the substitutions into it. Okay, here's what you're going to notice. There are no formulas in this list that have a variable to the 4th power. I mean, at best, we see some things that have p squareds in them. Okay, remember, p's are where the variable is. Okay, so when you see x's in this example, those are going to show up as p's here over here in the formula. Okay, here's what you need to keep in mind. Anytime you have an exponent that is even, that means it's squared, it's to the 4th, it's to the 6th, you need to over here find a variable squared. Okay, for example, if I take, let's say, an x and it's cubed, but then I square that, that gives me x to the 6th. Okay, so what I'm telling you is anytime your exponent is an even number, that can be represented as a variable that has been squared. So that's why if you see an even exponent, what you're really looking for, and I'm going to highlight this, when I see this x to the 4th, I need to be looking for a p squared in this spot here where that x to the 4th is. Okay? So let's see if we can, I mean, clearly this has a square root symbol in the denominator, and our goal is to try to pick a formula that has a square root symbol in the denominator and probably has a p squared in this location right here. And then of course the +1, I'd be looking for, a plus a or a plus b for a constant, something like that. Okay, so first and foremost, I need a square root in the denominator. Okay, I am not seeing a square root in the denominator for formulas 9 through 12. So those are off the table as options. Okay, let's see here. There are no square root symbols in the denominator for 15 or 16. Okay, in fact, 17 has no square root in the denominator, so that's gone. 19 has no square root in the denominator, and 21 through 23 are exclusively for natural logs and e's. Okay, so at least we've got it narrowed down to either 13, 14, 18, I'm just going to highlight our options, 13, 14, 18, or 20. So let's see if we can't kind of hone in and through process of elimination. Remember, we are focusing on the denominator only right now because that was the more complicated aspect. not only do I want a square root in the denominator, but I need under that square root to have a p squared in this location where my x to the fourth is. Well, that's going to allow us to eliminate some other options, right? There's no p squared in the underneath the square root for 13 or 14. So, I'm down to 18 or 20. Gee, it kind of feels like the denominator of 18 is a really good fit. Now, you'll notice when you look at this, see how there's a plus or minus in between this p squared and a squared? That means this formula 18 works whether there's an addition symbol in between these or whether there's a subtraction symbol. In this particular problem, it is an addition symbol. That means if we go with formula 18, over here on this side, you're going to replace any plus or minus symbols with just addition symbols, okay? I think let's try 18, and I realize the numerator is not a match, but we were just trying to get the denominator to match anyhow. So we're going to go with number 18 for this example here, okay? So I'm going to write down formula 18, okay? And then I'm going to write down how formula number 18 looks generically, okay? So I'm going to write down, and I'm using an addition sign where it had a plus or minus. I'm doing that because this problem had addition right there, okay? So I'm just writing this down generically. I'm using a plus anytime there's a plus or minus. Okay, now my third step is to decide, okay, what are my substitutions? Because the goal has to be after I make my substitutions for the p, for the a, and for the dp, I need the problem to then match this original integral exactly. Okay, now I'm not just going to swap the p out for an x. Okay, I need to think to myself, what's something that I could replace in here for the p so that after I squared that, it would then look like an x to the fourth, okay? Well, if I replace the p with an x squared, then when I make that substitution, I'll be substituting an x squared here, and then I'll be squaring my x squared, which then will make that an x to the fourth, okay? Anytime you do a variable substitution, you need to take the derivative of both sides of this, okay? So I'm going to be substituting in place for the dp, a 2x dx, and then obviously the a, see how it was just a 1 here? I would want to substitute a 1 in for the a so that when I square a 1, it stays 1. Okay, so let's go ahead and try that here. Let's take all three of these substitutions. I'm going to make those substitutions on the left-hand side first. Okay, so x squared is going in for the p, 1's going in for the a, and 2x dx goes in for the dp. Okay, now when I do this, this is going to slide over here into the numerator, or at least the 2x would, okay? So I'm going to put that 2x here. That's going to make this x to the fourth plus 1 dxg. It looks like what I have on the left side is almost matching the original problem. The only minor difference is there's a 2 here and there's not a 2 there. Okay, that's a pretty easy fix, okay? If I don't want that 2 there, I'm going to multiply by 1/2. That's going to cause that 2 to cancel, okay? Now you'll notice I didn't write the right-hand side of the formula yet. I was just waiting and making sure that I could get this to match exactly. Okay, so I'm going to go ahead, I put that 1/2 there. Now, as soon as I put that 1/2 on the left side, I really should immediately do the same thing to the right side and put a 1/2 on the right side. Okay, and now I think I can come back to the right side of my formula and make my substitutions. Now, be careful. Remember, every p is getting replaced, not with an x, but with an x squared. Okay, and every a becomes a 1. And then you do have that 1/2 in front because we had to make that small adjustment by multiplying by a 1/2 right here to get that 2 to cancel. Okay, let's try one more here. Okay, so our goal is to try to pick what we think the most complicated part of this integral is. It's definitely going to be the denominator. I'm also going to draw your attention to the fact that, see how there's a t to the fourth there? We should look for a p squared in the formula for that spot there. Okay, we want to look for a p squared. So let's go back to the front. Okay, we're going to go back to the front here. Okay, I'm just going to do a quick erasing of a lot of this other stuff that I had here so that we don't have that kind of cluttering this up. Okay, oops. All right, and here is our problem, just so we have it to look at here. Okay, this was a t, 9t to the fourth minus 1 dt, and we agreed that the more complicated aspect is definitely the denominator. And so I want to try to find a denominator that's going to match this denominator, but I would want like a p squared to maybe be in place for this 9t to the fourth possibly. Okay, so I'm looking, I don't want square roots, we can get rid of those, so it's not going to be 13, 14, 17, 18, those aren't good. It looks like it's not going to be 19, 20, 21, or 22. So we got it narrowed down there. I need a p squared in the denominator, so it's not going to be 9, 10, 11. Doesn't feel like 12 is a good fit. Okay, now look at the order of 15 compared to 16. Here my variable comes first, minus a constant squared, as opposed to 16, it's the other way. It kind of feels like maybe 15 is a good fit for this. Let's try it and see how this turns out here. Okay, so I'm going to write down, I'm going to try formula 15. Okay, I'm going to go ahead and write how formula 15 looks generically here. Okay. Okay, now I'm going to write down my substitutions, and here's where this can be a little bit tricky. I know that this is a t to the fourth. It does have a 9 in front of it. You'll notice, though, in the formula, there wasn't an a or a b, c, or d in front of this. So when we make our substitution for p, we're going to incorporate what we would need to square so that it would become a 9t to the fourth. Okay, well, if we took a 3t squared, I'm going to do this off to the side, and we squared a 3t squared, that would become a 9t to the fourth, okay? So we're going to replace the p's with 3t squareds. I'm going to take the derivative of both sides here. We're going to replace the dp that's right here with a 6t dt, and then the a looks like that would just be a 1. Okay, so let's make these three substitutions. I like to do the substitutions on the left-hand side only at the beginning, just to see if it kind of feels like this is going to be a decent match. Okay, so again, I'm going to take this 6t here, slide that up to the numerator. And this is going to be 6t in the numerator. I get my 9t to the fourth minus 1. That's looking good. The only thing that's not quite matching is I've got a 6 here in front of the t. And if you look at the original, there's no 6 there. Okay, but that's an easy adjustment. I can just multiply by 1/6 to get that 6 to cancel. But if I'm going to do that to the left side, I have to put a 1/6 on the right side as well. Okay, now it's feeling like my left side of my formula is a perfect match with the original problem. So I can go back and say, I'm going to take now this right side of my formula, and I'm going to show all those substitutions. I'm making these three substitutions. Be careful, your a is a 1. The p is a 3t squared, okay? Okay, and then I'm going to distribute that 1/6, and that's going to make that a 1/12. Okay, I know that this is not easy. I hope that you guys will reach out and ask questions, and we're going to have a Google Meet on Wednesday and another one on Friday if you want to dial in at those. Okay, there's just 4 problems here for you to try today. Those 4 right there, it's on the agenda as well.